леко ангелчето да търка малко.
Very basic stuff.
Той има ли постоянен кабинет? Моя. Там са мога да кажеш на хората, искат да говорят, не мога да търсят.
Наши апликации са 7,4 ли?
Може да почва.
Okay, it's my pleasure to introduce Dr. Andrei Benguş-Lasnier from Paris, who he is our new postdoc here, new addition, and Andrei will talk about singularities, resolutions, and valuations. Andrei?
Thank you very much. So, as stated, I'll talk a little bit about singularities, their resolution, what it means, and I'll try to bring about how and why we use valuations. And of course, I'll explain each of these steps. So, first of all, let's do let's go for some motivations. So, I come from rather more algebraic background. So what I generally study are algebraic varieties. Right? So what are algebraic varieties? They are basically some kind of topological sets, but locally we can basically cover the whole thing by affine open sets that are given by algebraic equations. So where does this F come from? We have a base field, right? This base field. Okay? So we'll take n copies of it, and F will be given by n polynomial expressions. Like that. Okay. And we look at U as the zero set, zero locus of these polynomial expressions. So when you have this type of situation, so imagine that K is R but since we like to do algebra, we also like to have an algebraically closed field. But we can also have finite fields or finite algebraic closures. Finite fields. Of course, there are many other fields, organic fields and stuff. So, what do we want to say is that sometimes we want to consider this u or x maybe simply like a geometric object. So we want to get as close as we can, to a manifold. So we want to study its tangent space. So if P will be a point of x, from now on I'll consider myself that I'm in Kn, then P of x will be its tangent space, will be the place of elevation of n linear forms, where these are simply J. The differentials of the different polynomial equations. This is a P. Okay? So this is an affine space inside of Kn. Okay? And for now, this is a simple formal definition. If we consider its dimension over the field K of this tangent space, it will always be greater or equal than the dimension of the variety. Now, this dimension of variety usually is defined as the cool dimension. Okay? But since we have a algebraic variety, this is simply the transcendence degree of K of its function field. Okay? So this is the function field, so so consider them like the field of its meromorphic function. Basically, you have regular functions over x, or given by polynomial expressions, and you consider the quotients of these functions. So this brings us to the first definition that I want. At least this shows us what do we consider as a singular point or not. So P is smooth if how do I call it? Star is an equality and singular if otherwise. There's also another definition of regularity. Well, so our point will be regular if the stalk at that point will be regular, but I won't bother with that definition. I'll just say smooth and singular, and that will be just simply an equality of dimensions. Okay. So this is where things differ a little bit from differential geometry in analysis of complex manifolds. We are used to giving examples and counterexamples of what could be a smooth manifold or complex manifold. So some of the basic examples we usually get are nodes. Alright, so if I consider this like this is the equation. Alright, so this is y. This, I don't know if, can you see in the back? Size is okay? Okay. Other examples include nodes, cusps, actually, no. So this is, I was previous step, so x, okay. Okay, this is a cusp. So these are basic stuff and curves. As you can see, everywhere except at the origin here, everywhere else it's a smooth line. We can have some more complex examples, like for instance this following surface. So I'll give it first the equation. It'll be a little bit complex, but it's good to have some complex examples, just to see that sometimes our objects are a bit complex. So I've drawn a referential, and in this referential I'll have the surface that is given, well, a section of the surface, because I can't represent all of it. This, I can see everything. Okay? So, what I've represented here is actually something of a mixture between these two. So, I basically, so this is x, this is y, and this is z. So, if y is different from 0, I can get a hyperplane section, which is a node. And if I go through the origin, I obtain a cusp. So what I've drawn in red is the singular locus. So the singular locus is simply put the place of all the singular points of this quite interesting surface. And at the origin, we also have a very special point where the two types of, let's say, singularities meet. Because having a nodal singularity and a cut singularity, it's a different thing. So it's a junction there that happens that is quite complicated. Okay. So this is the kind of object we study. And, well, sometimes it's kind of problematic because we usually wish to have a smooth variety so that we can have so there are many problems because we can't really do the usual geometry we would like to do on these types of varieties, right? So if k is equal to r c, around the smooth point, so f, the defining function, is a submersion, right? And in a close neighborhood of P, X is a smooth variety, smooth or complex manifold.
Excuse me, and is a what? It is
a submersion.
No, the next line.
And in a neighborhood of P, it's a, yeah, sorry, it's abbreviated.
Okay, maybe because the board is wet, I couldn't figure it out.
Sorry. P. Then around that point, it will be smooth, and there. So, but on a singular variety, we can't, or with great difficulty we can do it, but usually we cannot define easily many of our the optimals. So we can't have singular cohomology, or at least it has pretty strange properties like duality fields. We don't have Chern classes. Chern classes are very difficult to define. Singular variety. And also, yes, one of the things we really wish to do and do explicit computations are intersections. Intersection theory, we know how to do it very explicitly on regular surfaces, but in general, it is a pretty difficult question to answer. So what do? We wish to say, okay, well, I want to obtain, I want to modify X. I want to keep working with singular varieties because there are so many of them. But I will try to reparameterize the varieties so that I know that so that I at least can have something of a smooth variety which is sufficiently close. So so this is the first term that I'll define in the title. Well, no, the second already defined. So a resolution of singularities. What is it? Well, if X is a proper birational morphism Y goes to X. And of course, I'll define what I mean by proper and what I mean by birational. At least give you an idea of what we're looking for. So this is to trying to reparameterize X, with Y smooth. Y smooth meaning that every one of its points will be smooth. Reparameterize X by smooth. Of course, we can do it however we want because we wish to preserve some of the inner geometry of X. So if X will be compact, we would wish that Y would be compact as well, and so that when we want to define something on X, we can define it to Y, so that these invariants will be pertinent or relevant to X as well. Okay. So let's see what does birational and what does proper actually mean for us, so that we get an idea of why it seems like a relevant idea. Okay, so what does birational mean? So if I'm going too fast. So this is birational if I can find an open dense subset of X in X such that the induced morphism S is an isomorphism. So Y and X have almost all of its points very similar, right? But since we work with such algebraic objects, it turns out that we can actually give a different definition, which means that or the induced, so let's see, y, x. So if we have a morphism from y to x, we actually can induce a morphism from y, from y to x, from x to y. How we do that? What I said, the basic idea is that I said that k of x is the set of, let's say, meromorphic functions. So we take a meromorphic function from x, and we can actually bring it back to y, thanks to y. And this needs to be an isomorphism. The induced is an isomorphism. And reciprocally, if we have an isomorphism between the function fields, we have a birational morphism under the lattice. Because we just need to imagine that actually pi is not given by, how you say this, regular functions, but by quotients of polynomial expressions. Okay, and what does proper mean? Well, proper would be the one definition I'll make mostly hand wavy, because I'll need to introduce the real object a little bit later. So, I have a morphism from y to x, and I want to say what is a proper morphism. So, imagine we have a discus, okay, that embeds in x. And I take away its origin, right? This is a formal disk. Actually, it does correspond to a real disk if we do complex geometry. But when we want to do more general stuff, we use valuation rings, but I'll introduce valuation rings a little bit later. So imagine we have a disk, and we take away its origin. But let's say that this originless disk is inside of y, and it projects to somewhere in x where the whole disk is present. But it turns out that the origin is also in y. What does it mean? It means that if I have this kind of square, where we have the simple inclusion here, our morphism here, this is somewhere in y, and this is somewhere in x, I can actually find the point, I can lift the point, the origin of this disk in x, in y, via y. So the idea is to see that there are no missing points. This is the basic idea. So it's a little bit mysterious to say like this, but to give an example where things don't work out, this is an example actually. If we have a disk here and there's the origin missing, well, we can't lift the morphism to itself. Okay. So why do we need this property? Well, it kind of rules out some very trivial types of morphisms, right? So this is a proposition, but it's more of a remark. Is that if sing of x is the singular points of x, then x, the smooth points is dense open subset of x. And this, well, if you consider the complex topology of a complex analytic variety, it is the sense, but in general, it's homogeneous topology. So, A proper map will be subjective. So we rule out morphisms of type well, we have x here, we have x, we get out outside the singular locus. This is data resolution singularities. Just to say that finding an actual resolution is not such a trivial thing, right? Like that.
Isn't it possible that X is entirely singular?
Sorry?
Isn't it possible that X is entirely singular?
Oh, that the point? No, actually.
So if you're looking at the reduced...
oh yeah, we look. Sorry, we are looking at the reduced variety. So this this doesn't happen. But indeed, yeah, if we consider closed variety, we take, given by an ideal I, we consider I squared in terms of schemes, and yeah, it gives you entirely singular. But we only look at singular, reduced varieties. Okay, so what kind of progress has been made to this day about this type of offices? Well, I'll try to give you a little bit of some historical lines, right? Just to give you a little bit the inception of the idea. Actually, we started resolving singularities even before we realized what we were doing. At least that's how I considered it. Newton gave us the first example of resolving plane curve singularities. Newton and plane curve singularities. Well, usually, originally that's not what he wanted to do, but that's concretely what he did. So what he did was consider a complex polynomial in two varieties. So this gives us a planar curve, okay? Just consider the zeros in x and y in C2. Such that, okay, so we can arrive at these conditions. I'll have, okay. If there's a monomial in F of type y to the power n, so there's with the non-zero coefficient, right? And we can always arrive at this situation via a linear change of variables, very easily. Right? Well, the zero part is true. To find the y and monomial, there's a little bit of work to do, but it's high school algebra, basically. And if we have, well, sorry for the alternating sides of the ball. So what does, if you have this situation, what happens then? Then there is a Poisson series expansion f a root f a y root of f. Now, what does that mean? That means that we can write y in terms of a power series of x, starting at 1, okay? But we need to take fractional exponents, right? So C, I will be complex numbers, and N will be such that, okay, f of x, y in terms of x is equal to 0. There. And this was the first. So, what does this actually mean? This means that we could find, so the curve given by f will have branches. Okay, so the curve will have different types of branches, right? And the y of x will be one that parameterizes one of these branches, right? Given by this. Also, all these, everything around convergence is quite alright. If f is either a polynomial, like I said here, or a convergent power series, then we can find y that is also converging around 0. So there's no real problem. And how, I won't really show you how we did it, but the idea was to simplify the Newton polygon associated with. That's to simplify F's, what we now call Newton polygon. And this is what actually he coined. He really was the one who preceded this concept. Some people actually use it also in number theory for the p-adic expansion numbers, or to study the p-adic numbers and the relation to roots of polynomials in terms of p-adic numbers, but this is a slightly different version. So, how do you define a Newton polygon of f? Well, so, this is the only place I need to write its monomials. Like this. Okay. Then, the Newton polygon in terms of y, okay, so this y here is quite important. And really, there's no standard notation for the Newton polygon. This is just one of them. So, it will be a convex hull of something a little bit more complex, but I'll give an example right below. So, I'll take all the indices where this is non-zero. I'll take the point of coordinates in the in R2, yj, and I'll take the first quadrant in ij, then the whole convex. So what does this look like? Well, I'll draw one example. So if f is y7, so we have a monomial like this one, plus y5x plus y3x squared plus y3x5 plus x6. Okay, so hello. Oh. So I need a little bit of coordinate points, but what we have here, this is 6, this is 7. Okay, so this is given by the monomial y7. Okay, x6 is here. Okay, or just 2 of them just to see how it works. Then we have y5, where we get down and 1. The next one is also aligned. We have almost all points. We have only this one, so it's y3, but here. Okay, so we have all these points, and as we said, we consider the biquadrants, right? This, and this. But we need the convex flow of this. So basically the convex flow, I didn't have, will be given by this thing. Okay, and everything here. So you can, as you can see, some of these points are not quite pertinent or relevant to the study. And the idea was to study the leading edge. So this is the leading edge. Okay, this is the leading edge of the polygon. And the idea.
Basic question, but what's the definition of a leading edge?
The leading edge. Okay. Well, it is when you consider, so that if there's a y monomial here, there's always a point on the y-axis. Okay? And the leading edge will be the edge of the polygon starting from this point.
And that's always true if we have a monomial depending only on y.
Yeah.
And what happens if we don't have such a monomial?
We come to this situation.
Okay.
We just try to find a good linear change of coordinates just to arrive at this situation because it's not isomorphs.
Thank you.
And, okay. And we proceed by considering only the monomials that are on these, on the leading edge, okay? And the objective is, is to define, how did I, okay, yeah, a change of variables, this time not necessarily linear, change of variables, such that the polygon looks like just this time it should only look like this. If we have something like this, then this edge would say that y is actually a y equals 0 is a solution of But in order to arrive at these transformations, we might need to do an infinite number of operations, and this is why we need Puiseux series and not polynomials. So I think this is a really interesting example because this is the really first time we see the methods of resolution singularities appear, and actually this is also the first time the subject branched out. We had several different approaches to the resolution singularities. The first philosophy was actually very close to this one. It was basically to associate maybe complex invariant, because this can be seen as an invariant. So, first philosophy was associate invariants of combinatorial nature, usually combinatorics. That we simplify by, well, there are different names for these types of, I've put it a little bit under the rug. These change of variables, what I want them to be, usually are blow-ups or monoidal transformations, usually blow-ups. They usually have different types of names. They also have quadratic transformations or quadratic. So there are many. There have been. This school has been quite successful. We had the Italian school, okay, with Bergolevi, Albanese, even Castelnuovo. Bertini as well, but the most successful result we have today has to be Hironak as a main result. Okay, so 1964 he published his seminal work entitled Complete Solution. In characteristic zero. Characteristic zero. So, characteristic zero, so that's the field K I was working with. It needs to be characteristic zero, algebraically closed. The proof was quite complex. Not many people really have the time or the courage to go inside the details of his known papers. They are compiled. There are more than 200 pages to decipher because they are. He really does one breakthrough after another. So many people have simplified, tried to find alternative ideas, but they usually come back to this type of idea. Now, the second type of idea I'll try to sketch was to use valuation theory. Now, this was actually taken about by Zariski. He is really the one who motivated a lot of the work in singularities. But his idea was implicitly already done in Riemann's work. When Riemann's abstract variety, meaning that when you have a just like we had with Newton, we had a equation. Riemann associated a variety, a Riemann surface, actually, to this equation, and this is actually a resolution singularities of the solution set of that equation, actually. And Zariski made a very an abstract version of this idea via valuation theory, and then it was taken about, it was pushed forward by Abianca. And later on, well, once Hironaka's result kind of made people to forget a bit about valuation theory, but then it was taken about again by Cossard and Pelton. By Temkin, Spivakowski, in recent times. So I'll try to sketch in the few minutes I have here why we are interested in valuations, and a little bit about how we, how do we frame the problem in terms of valuations instead. So this comes at a certain price. So this was framed via the local uniformization problem. So the idea is to abandon at first global solution, but to divide the problem into two steps. First, we try to find a local solution, so we take a singular point, local solution, and then we try to patch all these solutions back together to form a bigger variety. So, the idea, yeah, so if we have a singular point here, we try to find a transformation, global transformation, no matter, that only solves, that basically deforms the point into something which is smooth. But the idea is that the points that go from here to here, there may be many points in the fiber of the singular point. So how do we say that the point has been rendered smooth? How do we localize really the problem? And the idea, how do we localize? How do we keep track of the singular point? This is a P. And Zalewski's idea was to use valuations. Well, actually, this is not the entire motivation for valuations, but we'll see why shortly. So, definition. So, evaluation on K is just a field, is a morphism of groups, is a group morphism, usually written nu or v. Let's just write it v. From A star to gamma, which is a totally ordered abelian group. Okay? Such that, so we know what happens if we take the product, the value v of a product is simply the sum of each terms. But what happens if I take a sum? Well, we don't really know what happens, but we at least want to have this. So this is the condition. And if this totally ordered abelian group scares you, just think for some k. Okay? Just think that this big gamma is just Rk for some k. So this is evaluation in broad strokes. And I'll give you just two examples. Okay? So I'll give you several examples. Just to not confuse with the variety, we have k of t, right? So the fractional field of a single polynomial ring. We define and A and K, just define I love this, I'm not used to it. So, so just define the multiplicity of the root A in a polynomial f, and then extend it to the fraction field like this. So it's the multiplicity, basically.
You have 12 more minutes.
12 more minutes? Oh.
Too much?
Too much?
No, too little, it's not enough. Oh, okay. I'll give just one more example, then I'll go to the idea of the Riemann-Zalewski space. Okay. So another idea is k base y, just to show you that we sometimes really need several copies of R here. So f, you can write it f of x times g of y with, okay? So we take out all the x's that we can factorize in G and set mu of f is equal to, no, this is well, and the y multiplicity of g of 0y. Okay? So you take out the biggest power of n of x, sorry, in f, and then you just take out equal to 0, the remaining parts, and consider its y-dot. And this is a rank 2 valuations in the given terms. So, okay. So why is this interesting? Well, because a valuation has what it's called a center on k of x. So we come back to our geometry. This would be the function field. Variation v on k of x as center a point P on x. If the valuation of its stock is positive, so what is this thing? This is the general function. We can see it as the general functions of the variety at P. So this is a subring of the function field. We can see it as a subfield of the function field. And we say that it has a center if this is positive and if this maximal idea, because it has a maximal idea, if it is a local ring, strictly positive. Okay. And this is uniquely determined. Is unique. And if you remember, I said that the birational equivalence preserve the function field. So if I go from here to here, the function field remains the same. And so the valuation doesn't change at all. And it turns out that the morphism is a proper morphism if and only if the center goes from here to a unique point there. This is why the proper definition of proper property, is quite important. And actually, a very interesting part is that if you remember the talk I did about formal disks, the formal disk is simply the spectrum of a valuation ring. So this is actually what it means. It means that if I have a valuation on k of x, the proper morphism is simply just something that I can find a center. Okay. And then Zaleski studied x valuations k of x with center on x. Okay? Plus it has a Zaleski topology. And he defined this kind of grid space, but in the abstract, for the curve, for the complex curves, this is simply the Riemann surface associated to our writing. Now this is a pretty big theorem, so it's Zaleski and Chevalek. So there is a continuous map from the Zaleski space to X, and its topology is compact. So this is quite interesting for a simple reason, is that if we can solve the local uniformization problem, we can find a point, we can smooth out points. Since the non-singular or the smooth locus is open, we can find an open covering of the Riemann-Zaleski space from which each open sends to smooth points. And since it is compact, we only need a finite number of valuations to uniformize. So the idea is we need to uniformize just a finite number of valuations. There you go. So then remains the problem of patching things together, but that we only know how to do it in characteristic 0 it is good for every dimension. Unfortunately, for positive characteristic, we know to do it very well for surfaces. There remains a lot of technical problems in this area. So my field of study for my PhD was mainly to study valuations of these types of fields, of function fields. So that's our study. Sorry for the opportunity.
Well, you still have 5 minutes.
If you have any questions or if you want me to maybe
any questions?
Details.
May I ask again the importance of this theorem for the calculation?
Oh, the compact part. Okay.
Maybe you can also say how do we define this space?
I'll define the space.
So, I mean...
Well, there are actually two ways of defining the Riemann-Zariski Riemann. There's no canonical reason. So we can actually just simply define it as the set of valuations on the function field, okay, which have a center. But if we have a variety of varieties complete, meaning that it is proper, so it will, any valuation on k of x will always have a center on x, if it is a variety, a proper variety. But there's also an alternative way of going about it. Okay. We can also define the Riemann-Zariski space in a pretty abstract way as a projective limit, actually, over x alpha, where x alpha will be all the proper birational morphisms above x. So this, you think that maybe if I take a projective limit, I can obtain another of schemes, I can obtain a scheme, but it turns out that this space is infinitely more complicated than that, actually. We only really know how to describe this space very explicitly in dimension 1 and 2, and it's fibers over hypersurfaces. So if I have x over y, where this is a codimension 1, codimension 1, then I can consider the fiber over a point. The fiber of a point in here, inside of here, has a very complex structure. It has the structure of a real infinite tree. Right? But yeah, the topology of the fibers of these types of morphisms have there's Annabelle de Felipe. She wrote her PhD on this. It's very complete and she gives very sharp results on how to describe these fibers. And basically, these types of structures are called valuative trees, and they are very complicated to study usually. But this was actually one of my attempts, was to find parameterization of these trees. Finding parameterization of these trees gives a hint about the structure of how we can uniformize valuations.
So maybe Doctor's question was about the relevance of this to resolution of...
Oh yeah, sorry. Yeah. So if it is compact, why is it so interesting? Well, Since the patching problem is so complicated, we wish to have a small amount of quantities to patch together. And it turns out that this compacity gives us a finite number of models to patch together once we uniformize. So how do we proceed this way? Suppose P is the next single point. Okay? Then if now I'm changing direction. Anyway. And it is sent, and say that the center V is P, and then the center is P prime. Okay? And it's smooth. Then, as you remember, I said that the smooth locus is open. Okay? So there's actually Y, which is smooth, the smooth neighborhood, meaning that all the points inside of this open are smooth, okay? And if I call this sigma, okay? I just consider sigma minus 1, the reverse image view by sigma is up. Okay, is also open because this is continuous, and well, you kind of the Zensky topology actually you kind of build it to be continuous. So this will be an open space, and you can cover if the local uniformization is always true, you can cover zeta of x by these types of opens. But since it is compact, we can just consider a finite number of them. And if you can consider a finite number of them, then it means that, let's see. Well, means, so let's say that this is associated to point P, this is VP, so V of Py, so okay, so we have only these opens and a model. So Y will be called a model, so just make sure. Model Yi over X. So you could consider in some sort of way that this would be some sort of resolution. Every point we here will have an index I where its images will be smooth. Here. So that then all you need to do is to patch these Y together in a proper rational model. But this is the difficulty of finding the patching problem. Olivier Picton, he axiomatized the idea of patching in one of his recent papers, but there's a lot of work to be done in that area.
And the ultimate goal is to find the resolution in kind of positive characteristics.
Exactly. This was the method that we wanted to implement for positive characteristic resolutions in practice. And Cossin and Picton actually used this strategy for, well, they completed the proof of surfaces and freeforms. And in positive characteristic, this is all we do. This is the limit of the thing.
But wasn't it known due to the work of Bianca?
Bianca, the surfaces.
Yeah.
He did it for surfaces in all positive characteristics except 2, 3, and 5. Because he used an auxiliary problem where he reduced the complexity of singularities, which for freefolds needs, the characteristic needs to be slightly bigger than 6. And we needed to complete these remaining cases, and it was very technical. Abiancar really made an incredibly complex proof, 500 pages in total, to work out this problem. It was simplified. Kutkowski wrote a very nice article where he simplifies all this work, but it's still a very technical problem. It's very
Okay. Other questions?
Yeah, sorry, are you using ZR of Y rather, or are you pushing it fully back to the zero base? This sigma.
Sigma, yeah. No, this was sigma was the
map from, say, X to ZRX.
Yeah.
The U lives in Y.
no, sorry.
From 0x to x.
From ZRX to X.
Yeah.
Projects down to. This is simply the map that assigns to evaluation its center.
How about U? U is an open set in Y.
In Y, yeah. Yeah.
What's the meaning of that?
Well, the idea, the thing is that the Riemann-Zariski space only depends on the function field. So, yeah. Since all of these maps are
Oh,
probably...
they're the same. ZRX, ZRY are the
Yeah.
same.
And the centers really have a clear correspondence since it's proper map.
So if you have more questions, you can find Andrei in room 325, that's his office. So let's thank the speaker again.